Today I'm going to talk to you about this shape, which is a 2D quantum lattice spin. And why did I stumble upon this shape? Well, to me, shapes are very important when it comes to neural networks. And the shape of the neural network, the shape of the environment that the neural network is in, all of these have impacts directly on the training of the neural network and how well it performs after training. And to me, I break this up overall into, first of all, we look at the dimensionality of the space, right? So we look at, first of all, we look at like Euclidean space would be our base space, which is infinity space, right? So Euclidean space has no boundaries in of itself. It's like a flat line with no start and no end. And that's a good way to look at Euclidean space, like one or two dimensional, right? But infinite. And then you have spaces like spherical space, which is like 3D space, and then hyperbolic space, which is also 3D space, but 3D curved space. Or hyperbolic space can be multidimensional space, a higher dimensional space, but it's curved space, would be a simpler way to put that. And then you have fractal space, which is like its own entity and its own beast of its own. And I don't claim to be well versed at all overall in fractal space and kind of the characteristics of fractal space overall. But so what we're looking at here is a structure that exists within Euclidean space. So this is a Euclidean space structure, but it's a graph structure mapped to the space itself. It's like the best way that I can put this, right? So it's a graph structure, as you can see, all these individual nodes, so 0, 0.0, 0, 0.1, 0, 0.2, 0, 0.3, up to 0, 0.6, and then they represent columns and rows, right? So 0, 0.0, 1.0, 2.0, 3, 4, 5, and 6. And then it goes 6, 1, 2, 3, 4, 5, and 6. Exactly like you would expect, right? Like you can look at this like a chessboard or anything else. But what is unique is that you have this hollow circle in the middle of these four connections. And that hollow circle is a shape in and of itself, right? So this is the shape. It's a lattice, like a grid, with the hollow circle, like the hollow center, and that's like what it is overall. Like that hollow center is called a qubit, and then that's what our shape is overall, right? So this first block is very straightforward. It's just creating this shape. The first thing I'm doing is creating a lattice. So 7 by 7 columns, and then I have distance in between the columns, which is a distance of 1 in between. So there's space in between the columns. And then we have our 2D lattice graph, and then we have those auxiliary qubits, which we're putting in there. So we're just defining those, and then we're just giving it colors and visualization, right? So very straightforward. But to me, when you look at this shape overall, it lends itself very well to a graph neural network or to like a node-based structure, right? That's what it is. And then so my very first thing when I look at this space is I want to put a neural network in here. But first I want to understand like the dynamics of this space. And then so like kind of the very first thing I do like when I'm testing out these types of spaces is I test the physics of the space. In this first example, I test entropy within the space, right? And then so that's all I'm doing is just very straightforward. Within this lattice structure, I'm taking out the qubits within this first test and then just understanding how entropy works and how entropy works over time. And you'll notice here I'm extending this out to 500 because I noticed initially my test was 250, and I noticed something very strange within this, right? And that's what got me curious within this is like, so entropy seems to be leveling out over time. That's what I wanted to test, right? So it leveled out over time at 50, and then I was like, oh, that's interesting. Let me see if that actually holds true, or if that was just, maybe like a unique pattern that happened there at 50. And it's not, right? Same thing. 100 leveling out, right? And then so that's where I go to like that bigger number, and then that's when I put it to 500, and what we have here, right? And you can see end result, it has spikes and it has variations and up and down, right? But over time, what happens is that the entropy stabilizes in this environment, which is very unique for entropy to stabilize within an environment, right? Like within a physical environment, entropy doesn't perform this way. Entropy will increase over time within like a physical environment, and then so this is what attracts me to different digital environments and different digital geometries is exactly this right here, right? The fact that I can control this as a lever just via this shape, and then via this shape is relatively stable compared to most other shapes, right? Like this shape is a beautiful shape when it comes to looking at this, because this is entropy stability. Like almost perfect entropy stability. It's fluctuating between like 2.9, and then these bottoms, these extreme fluctuations are we're still looking at entropy levels between 2.9 and 2.3, right? So it's still like the like most of the fluctuations are within like between like 2.8 and 2.6, so it's within like zero point 0.2, and then the broadest fluctuations that we're looking at here are 0.7, or the most extreme would be that 3 to 2.3, so 7 is the most extreme that we're looking at in terms of the fluctuations there. And then so the next test that I want to do is, so I test entropy and clustering overall, pretty much are the main two dynamics that I want to test. And then so the next test that I do is cluster dynamics over time, right? And cluster size evolution. And this is an interesting chart to me overall as well, right? Because this is like, to me, essentially, like what we're looking at here is we're looking at quantum mechanics when we're looking at, and when you combine both this and this is quantum mechanics and quantum physics, right? And that's what's occurring within this space. So essentially, like what my interpretation at this point by looking at these two is that this lattice structure that we're looking at, this lattice structure that we're creating within Euclidean space, is definitely creating a jar within Euclidean space, within this digital space, right? And this jar is essentially creating an environment where we have a perfect stability as far as entropy, and then a perfect stability as far as cluster sizes, right? Like it's we don't have runaway clustering, and then we don't, like, it doesn't ever get out of control, right? If the cluster gets too big, especially as it does here within the middle, it breaks up, it breaks itself down, and then it's same thing with the entropy, right? Like I don't see these types of mechanics in a normal environment. And then so just seeing this stabilization, it's again, typically within a physical environment, it's runaway entropy, it's laws of physics, right? And then, but within this digital lattice environment, this 2D lattice environment, it follows different laws of physics. And then these laws of physics are very beautiful, they're very stable. It's not an indiscernible pattern. To me, it's a quantum mechanical pattern. But so I'll leave that up there for interpretation. And then so next step that I want to do within this is exactly what I started off with, right? Like this structure is like this node-based structure seems to be very lending itself to a neural network. And so let's create a neural network based off of the structure itself. And then so with this neural network, I'm literally creating the neural network nodes as the structure, right? So the neural network nodes are those nodes. Like that's why I keep going back up to that shape. Like that shape is the shape of the neural network in this instance. That's what this code is doing, right? It's saying take that lattice, that 7x7 lattice, and then train it. like this is our model. We're training this, and then let's train this and then see what happens, right? And then in this instance, I train it on the fashion MNIST data set just as a default, and then I get 72.2% accuracy, which is very high for, like, unexpectedly high for this, right? And then so just to give you how good and how high that is, let me go ahead and show you. This is an example of standard neural network. So this is like the same size and like this everything else. It's just not, we're not utilizing that lattice, right? Is the only difference. And then we get 36% as far as the accuracy within this model. So 36% compared to 72%. And then this is just in the pure lattice structure. So this is with the lattice without the without those qubits in the center, without those little dots in the center. And then so last test that I wanted to do was, let's put those little dots in the center into this, and then let's see what that does as far as the performance. And then so we get a slight boost in performance here, right? So this one ends up at 73.28% accuracy, which is a boost in performance. And then it's a boost in the loss rate, right? So this loss starts at 2.15 and it ends at 0.81, which is pretty significant compared to this one, yeah, so 2.18 and then down to 0.89. So we get like another like 0.8% loss, right? Like, or another 0.8 in the digits of the loss there. And then like another percent of the test accuracy increase just by adding these little qubits, which is pretty significant, right? Overall, it's measurable, and we're getting something measurable out of it and showing it within it. So again, it's what we're seeing is that this shape overall is like the best. And then we can add on, adjust this shape more, just highlighting and letting you know. So within the physics of all of this, like this isn't like this lattice spin structure isn't the best structure that I've tested 100% so far. Within all of this, the 100% best structure that I've ever tested within any of this testing is a hyperbolic cube. And then it's just within a hyperbolic space, hyperbolic cube, and then that gets on this same testing like above 90% accuracy. It's the only thing that's ever done that, hyperbolic cube. But so this is the best performing model that I've ever done, and this best test that I've ever done within Euclidean space. Up until this point, I've had a hypothesis that you couldn't actually achieve these types of results within Euclidean space, but this shape itself proves me wrong. So what I mean, theoretically, my assumption now is that you could get a model that could get up to like 100% accuracy or near 100% accuracy within Euclidean space, and then it would be possible. This shape is, again, like, so your default within Euclidean space is 36%. So we're doubling the default of to what you're getting. Like, and then I think you can double that again, right? If you double that again, you're at 100%. I think you can do it. I don't know what that shape would be. Like, maybe it's playing around with these qubits and these lattices, and then kind of strange shapes. I played around with Mendra sponges, all different types of shapes, but this one it's really cool. So just highlighting it overall, it's the highest performing shape that I've gotten within Euclidean space, 72%. I'll leave a link to this notebook overall. If you like this type of content, please like and subscribe. Thank you very much.